Good morning, everyone. Today we continue our PoligonSoft free classes, and we'll be discussing a topic not covered in previous sessions, mold creation within the PoligonSoft program, specifically in the master module, using only its built-in tools without external CAD systems. We'll be working with this model you see here, which is a sand cast iron casting. It's a fairly large model, already has its own mesh containing 193,000 polygons. This means that for creating the mold, we only have about 300,000 polygons left. If we had made the mold the usual way, meaning by drawing a box and generating its own mesh, we would never have been able to stay within the 500,000 polygon limit that the free version allows us to work with. However, we can't use the virtual mold for this part, because as you can see, it has many internal cavities that will obviously cause heat interference. For instance, this wall will heat the one opposite it, and the same applies here, plus there's an internal cavity that will also interfere with itself. So if we use the virtual mold for this type of job, the result won't be correct. We could have drawn a mold in a CAD system that repeated the external walls to simulate as if it were the sand mold, but smaller. But we can also use a tool we have in the program in the Edit tab, which is the Create Shells tool. Normally, the tool is used to create shells for investment casting, but it can also be used to create an area of sand around our part, which is the most important area for heat exchange. Normally, the heating depth of the sand isn't very large. That is, the sand heats up 120 millimeters into its interior, so we can, to avoid the errors implied by using the virtual mold, create something like a sand shell around our part. And then, outside of that shell, use the virtual mold to tell it that outside the shell we have the same sand, and this will give us much more precision in our calculation. Let's see how it's done. First, we execute the command create shells, and we see that we have several parameters here. Really, to create a coarse mesh, which is what we need, we'll access the settings and switch to user-defined mode. What do we need to assign here? First, we need to tell it the boundary index where our molten metal inlet will be. I'm going to switch to the boundary indices regime. For the entire part, we have index 17 set, which is the heat exchange index between the molten metal and the environment. So, to tell it that these two surfaces are a point where the metal enters, we have to select them and assign. Right now, we can choose any index. It doesn't matter anyway. It will change later. Let's say index 4. So, here we tell it, look, I already have it marked, that the metal inlet will be at index 4. Here, we put the volume index number that will be assigned to our mold that will be created. And here, we put the volume index that will be the cap on top. You'll see when we run the command. We'll leave it as is. We leave 2 and 3, meaning our sand will have a volume index of 2, and the little cap that will be on top will have a volume index of 3. The thickness of the layer we're going to create. Normally, it's always better here to put half the actual heating thickness of our sand. This part is large. It will solidify for a considerable time, so I'm going to put 60 millimeters here. Why 60 and not 120? Because I'm really interested in half. Meaning that if over here I'll have 60, over here I'll have 60, the total thickness will be 120. And outside, we don't care, because outside we don't have heat exchange. And even if we have 60 on this side, then we put a virtual mold and the heating will be correct. And the last parameter we need to assign is the quality of our mesh. This parameter isn't very obvious because the numbers are quite random. The minimum quality corresponds to the number 20, which is what we need to set. The maximum quality corresponds to 150. Since we need to get the coarsest mesh possible, we put 20, and now we can execute the command.
Done. I'm going to switch to the volume indices regime to see the difference. How can we see the program? I'll make a cut so you can see. How can we see the program? Has created a shell around our part, which is the shell to which we'll assign our material, our sand, to then do the simulation. Additionally, in the upper part, it has created something like a cap with very, very coarse triangles, which is the index corresponding to 3, this is 2, just as we had set in our settings. Now, the first thing I have to do is check if the mesh fits within our limits. I can see that I now have 500,418 polygons. I'm very close to 500,000, even exceeded. But now, when I delete our caps, which we don't need, we'll right-click here and select Delete. OK. As we can see, the program asks us, leave the boundary indices as they were, or set them to default. Here, we'll click Yes so the program recalculates all the boundary indices we have and assigns the correct ones. There, I switch to the boundary indices, and let's see what happened first. We check our mesh information, we can see we have 499,000 polygons, meaning we're good. We can perform the calculation in the free version. Now let's check what we have with the boundary indices. In the upper part of our piece, index 17 was set, which is the index corresponding to the heat exchange between the molten metal and the environment. If I turn off our mold, I can see that in the inner part, index 1 was set, which is the index corresponding to the heat exchange between our part and our mold. But, however, the outer index of our part corresponds to index 18, which is the index of heat exchange between our mold and the environment. I determine these indices by their color. If you don't remember them by heart yet, let's import, in the Heat Exchange tab, the default template for sand casting. And simply here, we can switch to the Project tab to see which indices are active. Right now, we have, as I said, index 1 for the surface where our part contacts the mold. We have 17 for the outer part, and we have 18 for the external part of our mold of the shell we've created. But what are we missing? We need to tell the program that out here we don't have air, but what we have is sand. How are we going to do that? First, let's make a second index. Let's say index 2 for a heat exchange index between sand and sand.
The heat transfer parameters will be like the parameters of an ideal contact. The material, in reality, doesn't have any type of contact. It's the same material. That's why here we put the heat exchange for ideal contact, which for sands corresponds to 10,000. We've created that here. We now need to go to the Edit tab, select all indices in the mold that correspond to index 18, and assign them the index we created, which is 2. Now, as we saw in the previous class, the one where we made the virtual mold, if there's no material outside the index, for index 2, the material, it will look in the material list for the one corresponding to 2. We close this. Let's assign the materials since I've switched to this tab. First, let's assign the material for our molten metal. Click Import. As I said, it will be cast iron. Let's select any one. The objective of the class isn't to do a real simulation, but to learn how to use different methods to do simulations. We've already assigned our metal material. Let's assign the material for our real mold, meaning for the shell we created. The shell is at index 2. We can see the little tab here, so here we need to import some type of sand. Let's use one of these sands. Let's say this one. I'll repeat again. What have we done? Now the program knows that for the index, for our part, this material is assigned. For the real volume we've created, which is the volume with index 2, this material is assigned. And since the external boundary of our real volume has boundary index 2, but no real volume exists outside, volume index 2 will also be used. This means that if I, instead of assigning for the external boundary, had assigned an index 3 here, for example, I would still have to tell it that I have sand outside. I'll assign the same one. But in this case, if I had done it this way, again, we'd have to say that for heat exchange, for index 3, I have ideal contact of 10,000. This name doesn't influence anything, it's just to know what it is. It can be done in two ways. Either assign two different materials, or simply assign here the same. Assign here the same index for which I already have the material. I'll leave it as I did. Nothing changes here. What do we have? We have the material of our casting, we have the real material of our volume that we created with the shell tool, and we have the material for the virtual mold that we created around our real mold. Actually, we could have assigned a heat exchange with the environment on this top surface here, but it won't influence it much because anyway the virtual mold works in such a way that it won't affect the exchange of this surface here. So we can leave it like this. We already have our calculation prepared, we just need to set the casting temperature. I'll check for this material. The liquidus temperature is 1173 degrees. So let's say the casting temperature is 1300 degrees. I'll leave the ambient temperature as it is, the mold temperature too. The last thing I need to do is set the number of cores of my processor on my computer that will be used for the calculation, in my case it's 4 because I don't have more, and execute. The solidification is activated. The calculation will be done with a 1-second step with an output every 10 seconds. Porosity is activated. Everything here is perfect. Now let's run our calculation. I save our model. As always, the program says it can't get the commercial license. It's completely normal. Now it will check the number of polygons our model has. And if it has less than 500,000, it will run anyway. And there, as you can see, it switched to the free module and started our solver. Since this will take a while, I'll wait for the simulation to finish and come back when everything is ready. We're back. Our calculation has finished, and now let's look at the results of our simulation. Let's go to the Mirage module. And first, we open our solidification, our temperatures. For that, we click the Open Temperatures button. We go to where our project is and open the file with the solid prefix, which corresponds to the temperatures in our part and our mold. First, I'll look at it without the mold. I'll set it to automatic playback mode.
As we can see, our part is solidifying. At a certain point, a massive hotspot forms here, at the bottom. It's most likely that some type of defect will form here, and similarly, in the upper part, we have an area here where there's liquid metal, even though all the surrounding metal is already solid. So it's possible a defect might also form here. And obviously, in the upper part of our piece, we're going to have problems, since it doesn't have any kind of feeding. As I understand it, it was supposed to be that, if we look, the upper part is thicker than the lower part. It was supposed that the metal in the upper part would simply be removed. Let's see the results and temperatures in our mold. As we can see, the mold heating occurs normally. There are no irregularities here. Our mold works as it should and gives us precise data in this case. Let's look at the porosity. Open porosity, and I open the corresponding file. First, I'll look at the porosities on the surface. This is the first step. There's no porosity here yet, so I'll skip to the last one, which is what interests me. As I can see, on the upper surface, as expected, we have porosities of well, here this is, I'm going to make a cut to see the internal part. We have porosities that are sometimes large, sometimes small. To see more precisely, I'll remove the cut and I'll set the isotherm with a porosity level of 5%. Here we have the final result. As I said, we have a problem here, which most likely can be solved by placing a type of chiller in this area. Same here. A small dot on the part that might be a calculation error. We always have to keep in mind that cast iron expands when it solidifies, and that process is very difficult to model. So porosity calculation results should always be taken as advisory. In the case of steels, porosity is calculated very, very precisely. For cast irons, it's always better to use solidification and not porosity, and keep this in mind simply for a superficial analysis of what's happening. And as we can see, in the upper part we also have defects. We're done with this. The objective of today's class was to learn how to make molds within the master module of the PoligonSoft program. We've achieved it. We've made a mold with very few triangles that, however, significantly increases our calculation precision and allows us to avoid using a virtual mold in cases where using a virtual mold isn't possible due to internal cavities or surfaces that exchange heat. I hope this information has been useful to you. We'll see you soon with new examples, new practices for working in our program. Goodbye.